Yeah, ironically, for the conference I came on Sunday, which was like nobody was here. Very few people, like except the local organizing committee, nobody was there. But yeah, I keep getting late to these talks. I don't know why. Maybe it's like some sort of curse. Right. Okay. Time series raster data with Postgres in PostgreSQL with TimescaleDB and PostGIS raster. This is what we're going to talk about. Just a quick again. Luca was already there and a few people were also there. Postgres. I've worked with Postgres a lot. That's the only database I've worked with. With other technologies that I've worked with are COGS, GeoTIFFs for handling a lot of satellite data, right? For a lot of rasters. So for that you need a separate service just to handle the Python packages and handling that data separately in a separate service, right? During that time, I was also, and we already invested a huge time in the Postgres infrastructure, building it up, distributing, had a distributed database cluster with more read instances, write instances. So we wanted a way to handle something in the database itself, right? So TimescaleDB is something that I was already familiar with. We were already handling a lot of time series data that was coming on a regular basis, right? And there were also a lot of rasters sitting inside in external storage. Right, so why not combine them both and see what comes with it, see what happens with it. What is TimescaleDB? So TimescaleDB again is an extension on the Postgres itself, you install it as an extension, and then it gives you better way to handle your time series data more efficiently, more reliably. We'll see how that thing works, right? Helps you with time series data modeling. They have a bunch of stuff that if you have time series data, it will always work with that. Automatic data partitioning, we'll see that. Continuous aggregate, amazing stuff. We'll see how that works. Advanced indexing based on the time series columns. Compression and data retention policies on your data based on the time, and ecosystem compatibility. This already comes with the Postgres, so you have all the power of the Postgres. Plus, you have the understanding. Plus, you have this way of handling the time series data. Postgres is great with working with relational data and with all the general amount of data. So time series adds on top of it, right? PostGIS raster. So in context of Postgres, you also have an extension called PostGIS to handle your geospatial data. Since this is a FOSS4G conference, so I'm sure all of the people know what PostGIS is. PostGIS raster is also there for handling all your raster data inside Postgres, right? Storing, indexing Postgres raster data along with geospatial capabilities provided with the PostGIS. So you can also combine your raster data with your vector data, doing spatial joins I want all the tiles within this particular shape, or I want at this particular point whatever is the pixel value. I can do all of that, and I can also do aggregating functions like mean, median, standard deviation for all my raster data as well. So just to quick read this out: storage of raster data, spatial indexing, raster algebra analysis, integration with vector data, raster tiling pyramids, and interoperability. Right. So spatial temporal. When usually I talk about spatial temporal, the idea comes from that we have an Earth which is constantly moving, which is constantly changing, right? So the Earth exists in the space, and then there is a temporal dimension where we're moving over and over again. Any data that you're going to be working with in context of Earth observation will have a temporal dimension sooner or later. I don't know if you're working with just a snapshot of the current data. You might be working with some sort of temporal data here and there. So that is why it just makes common sense to have a temporal capability to your database, right? That was the idea from where this thing came, right? And I was already familiar with the two technologies on a separate level, so I thought, why not combine these and see what happens, right? So rasters in database. If any of you know Paul Ramsey, he's one of the core contributors in PostGIS, and he recently had this podcast, I think last month or maybe this month, on Mathscaping, where he talks about rasters in database. He goes into really deep on what rasters in database are, why you should do it and why you should not do it. The ultimate conclusion is that you should not do it, because Postgres is not built for handling that kind of data. Just to give a little bit of context why it is, because rasters are very specific sort of like, when you're looking at a raster, you're looking at a static data. And you're looking why it is represented in the raster in the first place, because it's not easy to represent that huge volume of data in a vector format, right? If you're looking at raster of the entire earth for like say temperature, precipitation, if you try to put that data in a vector file, it will be huge, it will be massive. So that is why you put it into a raster format, which is like JPEG, PNG or TIFF or something, which is much more easy to work with and much more easy to inference also. So rasters in database, if you think you don't have a use case for it, don't do it, right? But it was, for me, why that was the reason why I wanted to put rasters in database was I wanted to work with the data. I wanted to join all my data which was already there in the database with the rasters that I had in someplace else, right? And ideally it would involve coming out of Postgres, querying those two separate data from separate sources, doing my thing, and then putting it in one of the places, either in the one storage or the other storage, right? I wanted to do something which would like keep me in the Postgres stuff. So, and then I can handle, then I'll have a problem. Obviously there are trade-offs in working with that solution and working with this solution, but I'm better off working with the trade-offs in Postgres rather than working with trade-offs of a separate service to build all this infrastructure, right? But yes, great podcast. If you want to get an intro of how rasters work in database, you should do it. Just a quick thing, underlying everything is GDAL, right? And Postgres stores the reference to the rasters rather than the rasters in a separate file itself. So GDAL just performs the functions on the rasters, whatever you're performing through Postgres, right? So if you're doing those same GDAL functions in your Python library or your other client, then the performance and more or less will be the same if you're just doing the raster operations. But again, not the best place to store your rasters. Right. Okay, I should have put it more because I already explained it why I'm doing it, why we can give it a shot. And there is hope, even if rasters are not supported in Postgres right now, it doesn't have that great of a support in Postgres right now, there is a possibility that there will be. And obviously when you combine few technologies here and there, you will come across use cases that you will be able to solve and contribute back to the project to make it better. Now, one such effort is what I tried with combining Timescale and PostGIS Raster, right? Okay, so getting things done, so this was just a brief intro of PostGIS Raster and TimescaleDB, what all brief, whatever theory I had. Next up, we're going to look at actual data and the actual SQL table and all of that. The two tools that I use is basically Raster to PostgreSQL, just to load the rasters in the database, and then QGIS to visualize the queries that I was doing and visualize the stuff that I was doing, right? A couple of things we're going to do. We're going to load the rasters in smaller tiles, build continuous aggregates to store inferences from the rasters, data and data retention and compression, right? Okay, so this is the stuff that we'll go with. I'll explain what continuous aggregates is later on, right? So loading the rasters in database. So by default, when you look at a raster, you have a resolution of X by Y, right? And when you load it into your database, you have the option of splitting it into smaller tiles. Ideally, you can store the entire raster in a single raster file, but you can also split it into multiple files. The larger tile size that the smaller tile size that you use for the tiles, it will take more time to insert that raster into the database, right? So you see so initially the rasters that I used was 2180 by 1080 resolution, and the first image is where I'm using 100 cross 100 tiles for that particular raster, and I've also placed a vector file, a shape file, which intersects with this raster. Right. So why it shows the area outside the shape? It's because this huge tile is intersecting with this shape. So when you are storing like a larger resolution tile, your intersect function will clip with the will not be a very great performance when you're clipping using the ST intersects, which is how we'll select the rasters when doing some sort of analysis or aggregation or whatever inference you want to draw from that raster, right? In this second one, so this is a 10 cross 10 tile. This is 100 cross 100, this is 10 cross 10. So you'll see it's much better, like you're selecting much less tiles, but like it's much better accuracy, but performance wise, I mean, they're more or less the same because it's like just one raster and very few values, but you have a better accuracy, right? So ideally you can also store one cross one, but I would not advise this because that's like a huge number of rows in your single table. And this is 5 by 5, right? And again, you have much better accuracy here than compared to this one, right? So it's all about selecting the tiles within a shape. It's a simple query where you like, I have a shapes table, I have a raster table, and I'm just selecting which tiles are there in this particular shape table, and then you want whatever you want to do with those tiles, whether you want to serve them to the customer straight away, or you want to do some analysis like we'll see mean, median, mode, standard deviation, and all that stuff. So this is what is the differences when you're loading the tiles, loading the rasters in your database, right? Straightforward, nothing much, just wanted to show you, right? So same raster, so 2180 by 1080 raster that I loaded had separate rows, the amount of rows that you're working with, right? So 10 cross 10, it was 157, 10 by 10, it's 7263, and 5 by 5, 26,000 rows. And I also did 3 by 3, it's not there in the list, it was about 60,000 rows, right? Which for PostGIS is not a lot to handle. Technically it can scale to millions or even billions of rows depending on how much infrastructure you're giving it. So PostGIS works great with big data, and I wanted to stick to PostGIS, so again, right? So this was just a spatial part of handling the rasters. We've just loaded the rasters in the database, done nothing fancy, just a bit of tiling, and that's it, right? Okay, so yeah, so doing the time series stuff. So once you have this table, okay, it's not that clear, but so you have the RID, which is the raster ID, and you have the raster, which is like a reference to the raster, and you also have a timestamp column. This is your normal raster table, right? Where you're just storing all the rasters. So what I showed in this particular slide, when you have all these rows, so this 26,000 rows lives in this table where you have an RID, you have a raster, and you have a timestamp. That's it, corresponding to that particular raster, if you're talking about temporal dimension to it. I mean, all I added was this timestamp, and I also indexed it with the timestamp, also indexed on the timestamp column. That's all I did, right? In contrast, when we have this table, which is like a standard table, standard PostgreSQL table with just a timestamp column. In comparison, we have this timescale table, which is something called a hypertable inside timescale terminology. What essentially it means is that it automatically partitions your table based on the timestamp. You have a simple function called create hypertable on your normal PostgreSQL table, and based on the timestamp column, it will create your temporal table, right? So again, fundamentally same in terms of writing your SQL queries for this table or this table. It won't make any difference. What the difference is that in your hypertable, all based on the temporal chunk that you specify. Like chunk is basically the size of this particular partition that you want to keep. It can be different based on your use case. It can be 1 hour, 1 day, 1 month. For this particular use case, I loaded rasters for last 20 years for world precipitation. I've also mentioned the source, right? For last 20 years, I loaded all the rasters. So it was about 264 files. And then I chunked all of them based on a month. So you can imagine 265 by 12 is the size of my chunk in this particular table. And when you're working with a lot of time series data like querying and inserting, this makes a lot of difference compared to a standard table with like timestamp. Your data is already partitioned, so your temporal queries will relatively work much faster. By default, partitioning based on the temporal, right? So yeah, that was the time series stuff. Just creating a hypertable so that you have data partitioning based on the timestamp. Next up is another time series concept, something called continuous aggregates, right? And so you look at your world raster, and you take all the rasters between 2001 and 2002, which is like 1 year rasters, right? And what you want to do is you want to calculate the summary over those rasters, which is like mean, median, mode, standard deviation. This is a standard PostGIS raster functions which calculates these values for the raster itself, right? So again, when you do this stuff, why it is said that it's not a great thing to handle rasters in PostGIS. This is very slow. This will take about anywhere, depending on your hardware, for anywhere from 10 seconds to 20 seconds. I ran it a couple of times. Sometimes it took 10 seconds, sometimes it took like 20 seconds, depending on whatever was there in the memory. So this took about 10 seconds, and I had like for the year-long inference on my raster, right? Something that I can do with the continuous aggregates is that I know that I'm going to be accessing this inference over and over again for an yearly thing. So what I did is I created, like, this is a standard, again, this is also a Postgres concept where you could create materialized view. What Timescale helped with this is that Timescale, the continuous aggregate is actually under the hood a materialized view only. But they handle the refresh part, and they also handle the time bucketing part. So for here, I just specify that I need the continuous aggregate for all the 1 year, right? So my continuous aggregate for a 20-year data, I'll have 20 rows with all these stats already stored in the table itself, right? So if I know that this is going to be a common use case where I'm going to be querying the data on a yearly basis, rather than calculating over and over again, I just store it in the continuous aggregates, and the Timescale handles updating and managing this materialized view rather than refreshing it myself, right? So it's just all of that. And in this particular example, you can't see it, but this also has a trigger where it's something called TS insert blocker. TS insert blocker, where before loading the data, it basically calculates which chunk to put it in, and it puts in that chunk rather than just putting the data right away. So in this way, I can create like 5-year chunks or monthly chunks or 15-day chunks, anything. Like all of that is handled just by this piece of code, right? And then I can query directly that chunk, that materialized view, rather than calculating it over and over again. Right, that was, I had another slide for retention and compression. I think it's not there. But adding the compression, so Timescale also has a compression policy which can really save you on your storage costs by moving the data, by compressing the data, by compressing the less frequency data. So if you have like a 20-year data and you're only most of the time you're only concerned about your last 5-year data, you can compress the 15-year of data to save some storage costs. And also the retention policy, if you have a lot of raw data coming in, like for example, like if you have a lot of raw data coming from, let's say you have an API request and you're storing each API request in your DB, but at the end of the day, you don't care about the single API request, you only care about an aggregate. So you can also use the retention policy to delete the previous data, which you don't need, which is never going to be used for analysis, right? And yeah, another thing, if you were there on my previous talk, Uber H3 indexing, right? This can also be applied to rasters to make it more efficient. I just read it in theory, and I'm gonna give it a try. So that's why, and you can also create like zonal aggregates with that. Like then you're talking about you want to split your rasters into multiple shapefiles. Like you have different country-wise statistics that you want to build from the rasters on a regular basis. So what you can do is create the H3 index, create those zonal aggregates, and put continuous aggregates on top of it. So you always have that ready in the database, right? From the previous talk, somebody asked me like, this is a lot of compute that we're doing each time we're inserting and updating the data, right? So my thought process is that when a user is querying the data, let's say the user is querying the data for a particular country, right? So what you're going to do, you're going to figure out all the pixels in that country, and then you're going to do your other computation and give that result back to him, right? If you know that is a common use case, and if you know that your product is built around delivering country-wide data or like aggregate data, then it makes much more sense to do that pre-computation and store it, right? In a traditional Postgres architecture, I'm assuming you have a separate read-write instance and a separate read instance. So you can have a very bulky write instance which is doing all this compute, right? And then you have a relatively simpler read instance which is just replying to the queries, which is not doing more compute than what it needs to. Right. So again, for inserting and building this continuous aggregate materialized view and like replicating a lot of data, where we are optimizing for the compute by sacrificing the storage, because again, the materialized view will take a lot of storage, right? And this is going to be the case for all your. This is going to be the case for all your thing. So I'll not read this out. I'll just move to the next thing. The sources that I've used to create this, all the data and everything that you can do, and the code, whatever I've used here, is in the Postgres, so is in the GitHub. You can go ahead and try. It has much more written queries that you can do and play around with it, right? Yeah. So that's it from me.